So, going to deal today with end behavior again and the dreaded application problems, which we are going to find out aren't really so bad. So we're going to take a peek at these first couple of end behavior problems. And you'll notice on all of them on this front part of the sheet that the x part seems to be done already. And the reason is, with the x part, it's always going to be 1 going to negative infinity, or saying what happens as x goes to the left, because, well, as we go to the left, numbers get more negative. And then as x approaches positive infinity, which basically means my x values are going to the right, because I want to see what's happening with my graph. And the only way to see what's happening all the way across it is to go from left to right. So when you get to the quiz, I'll warn you, those will be blanks as well, but you're going to know by then, since you've had some practice, oh, one's got to be negative, one's got to be positive. Okay, I got this. So the only part we're going to really be dealing with here is the f of x part, the y part of things. And again, when we're looking at the y-axis, as we go up, we head towards the more positive numbers, so positive infinity. As we go downward, we head towards more negative numbers, or negative infinity. So when I get to this point, I'm like, okay, so what's that mean? Well, as x is going to the left, so as I keep going left along my graph, which one of the values am I heading toward as far as y goes? I knew I'd spit it out. We're going down. We're heading towards negative infinity. And I don't care if you write the directions with it, up, down, left, right, but you've got to get the infinity in there. Okay, so then as I go to the right, which way am I heading? Still heading down, still heading towards negative infinity. And that's all I'm doing on these. And I can even read them back to myself at the end to see if it makes sense. Okay, y goes down as x goes left. Yep, as we go left, we're going down. Okay. Y goes down as x goes right. Yep, as I go to the right, y is going down. Okay, that makes sense. That works. Okay, we're going to do one more up here. I want to do the one right below it because some of my graphs, as I cut and pasted, I notice, lost their arrows. So if they're not arrows, that is not me trying to trick you. I'm just going to put arrows on the ends here so I don't get myself confused. So I've got the x part here ready to go. So as x goes to the left, which way are we heading with y? Toward which of my infinities? Toward negative, because we're going down again. Okay, we don't go down every time. As x goes right for positive infinity, this time I'm moving up. We're heading towards positive infinity, and that's all I'm doing on these. Just watching the end behavior to see what's happening, and I'll be set with those. So nothing too bad. Okay. The rest of this packet's going to be application problems with our different functions. So we're going to do a couple of these too to make sure we get you on the right track. So we're going to start with number 7 here. So we've got annual tuna consumption. Based on Census Bureau estimates, the annual consumption, no, not composition, we're not making the tuna, we're just eating it, of canned tuna in pounds per person, they give me an expression. And then the consumption of turkey in pounds, they give me another expression, where T is the number of years after 1989. Now let me explain what this last little statement means. What that means to us is, if you were asked, how much tuna did somebody eat in 1989? That's called my base year, since that's what they're doing here. And my T value for that, if I was going to plug it in, would be 0. Okay, my base year always is going to have a T value of 0. Now if I wanted a different year, let's say 1990, okay, that's 1 year later, so my T value would be 1. Or if I wanted to know what happened in 1995, okay, that's 6 years after this, so my T value would be 6, and so on. It just allows me to plug that value in and figure out in a particular year what that consumption would be. And businesses use numbers and data like this to figure out what's trending, what they should be selling or not selling in some cases. So on letter A, how many pounds of canned tuna and how many pounds of turkey were consumed per person in 1989? Okay, 1989. T is going to be 0. So all I have to do here, when I go to calculate this, is say, okay, so this is my tuna function. So C of 0, again, that's just a label. And then I start copying this until I get to a T. When I get to a T, I plug the value in. And the nice thing about this being the base here, being T equals 0, is anything times 0 is 0. So this all just turns into 0. So 3.87 pounds of tuna would be what the average person would consume that particular year. And then, since it also asked me for turkey, I go to the turkey one. And again, I just start copying the function until I get to a T. Then I replace it with a 0. And I work my way across doing that. And again, I like 0 because it wipes this all out. And I find out that the average person eats about 13 pounds of turkey. Okay, so kind of keep that in the back of your mind. It's about 10 pounds more of turkey than tuna, and we'll see why an application like this is helpful in just a minute. Then I get to the next part, because these are going to have several questions in each one. Find the difference between the amount of turkey consumed and the amount of canned tuna consumed. It doesn't give me a year, though. So what it wants me to do then, okay, what's a difference? Is that like add, subtract, multiply, or divide? Subtract. So we're going to do turkey minus tuna. So I go, okay, my turkey expression is right here. But then I want to minus my tuna expression. And I want to use the parentheses because I'm subtracting the entire quantity. I'm subtracting the 3.87 and the 0.13. Okay, not just the first one. So similarly to what we've done when we've gone to combine like terms before, I'm going to distribute that negative through. I'm basically just going to change the signs on each of these. And then I'm going to go back and I'm going to find like terms. And when I put it together, that's going to be my function for this total. So I notice there's only one term that has a t squared, so I'll just write that down. Then I go looking for my t terms. 0.8 and 0.13 would be 0.93t. And then 13 minus 3.87 is 9.13. So here's what this new function does for me. Now if I'm asked for a particular year, what's the difference in consumption? How much more turkey was eaten than tuna? I just plug those values in here for t and I get the answer. It's kind of nice that way instead of having to do each one separately. Well, it just so happens that this problem isn't quite done yet. When we flip to the back, it says use your answer in part B, excuse me, to find the difference in the amount of turkey and the amount of canned tuna you'd expect to be consumed in the year 2000. Okay, bless you. So I'm going to take that expression that I got in part B, so here's the question. What value am I going to be plugging in for t? If my base year is 1989 and it's now the year 2000, 11, because it's 11 years later. So I'm going to go back here. And everywhere that there's a t, I'm going to replace it with an 11. And I'm going to pop that into my calculator. And I'm going to get an answer out. And here's what I was kind of saying to pay attention when we were doing that first question. Remember, back in '89, there was like almost 13 pounds difference, or at least 12, I think, between the turkey and the tuna. Now in 2000, there's like barely over a pound difference. So tuna consumption's going up, turkey consumption's going down, and if you're selling food, you might want to think about this a little bit. You're like, why is everybody buying tuna instead? Is it because it's cheaper? Somebody found a health thing going? What's happening here? And you'd want to look into that more. And that's how you can use data like this actually to make a difference depending on what business you may be working in. All right, one more. I'm going to move down to 12 here, talk some college expenses. 3 major college expenses are tuition and fees, books, and room and board. And they're approximated by these 3 functions, so tuition, books, room and board. Where t is the number of years after 2000, so 2000 would be my t equals 0 value. Write a polynomial representing the total cost of tuition, fees, books, and room and board in t years after 2000, okay? In other words, they're just telling me to combine like terms. So I'm going to go back into my problem. I'm going to say, okay, where's my biggest exponent? Here it is. So I'm going to take my t squareds. I'm going to put them together. I'm going to take my t values. I'm going to put them together. And I'm going to take my constant terms, my numbers, and put them together. That would represent my polynomial. So no matter what year I gave you that occurred after 2000, I could plug that in for t, and then that would tell me what this particular cost is going to be. So for instance, okay, what was the cost of tuition, fees, books, norms, room and board in 2000? Well, again, 2000 is my base year. So I'm going to plug in 0 for t. Oops. Not that way, I was not replacing t. That's not the way to do it. That was a good example of how not to do this problem. So everywhere there's a t, I'm plugging in a 0, which again we have found to be a good thing because those are easy to deal with. This ends up 0. This ends up 0. So I find out it's going to be about $8,766. Now we can tell that was a while ago because I don't even think I could get tuition for that at this point. At least not like at a 4-year school. So, okay, what would you predict the cost of tuition and fees, books, and room and board to be in 2005? What's my t value going to be? 5. So I'd go back to that same expression. And I'd work my way through this one. And so if I punch that all into my calculator, I get that out. And again, that's all that I'm doing with that. So, not a bad deal. So I'd be able to go through with this and do it no matter what year it was. So like, I could easily do this and freak out if I did it for when my son would be going to college. My son, just to show you that sometimes we would have to tweak this information a little bit, because if this is true, I'm just going to go file bankruptcy. Just as a fact to say that sometimes we need to watch out for this. So my son would be graduating in the class of 2033. So if I went through, I just did this on here and it just made my eyes bug out. We probably would need to check our data again after a few years, because just for a funny, okay, that'd be a year of school in 2033. If that's the case, we're going to find something else to do. I don't think it's going to get that bad. So it just goes to show that sometimes we would need to recalculate this a bit, or Dad needs to go find a second job. Okay. So, your job, knock out the rest of this. The key is up front. If you need to spend some extra time, which I kind of tried to work in here, to work on some of the other stuff back into the week a little bit so you have that homework check ready next week, that'd be awesome.